Hello everyone. The title of this video is Derivatives of Transforms in examples. So hopefully, I'm assuming here that you know some basic Laplace transforms for polynomial functions, exponential functions, and sines and cosines, right? Basic trig functions. And then we're going to go from there, right? This will be an expansion of those. All right. So first, let me get into the rule here. So suppose capital F of S is the Laplace transform of some function of t, f of t. And we have n here is going to represent some positive integer. Right? So lowercase n will represent 1, 2, 3, 4, 5, etc. Then the following, and you could pretty easily verify this using the definition of Laplace transform. Remember that improper integral from 0 to infinity of e to the negative st times f of t dt. If you times the function that you're taking the Laplace transform of, dt. You could pretty easily show this using integration by parts rules, or just a differentiation with respect to s. So again, most textbooks will have a derivation of this. I'm not going to go into the derivation of this. So the Laplace transform of this f of t multiplied by a power of t, so t to the first, t to the second, t to the third, etc., some whole number, power of t. Well, this is equivalent to negative 1 to the nth power multiplied by the nth derivative of f of s, right, which is the Laplace transform of little f, with respect to s. Okay. So again, rather than go and using the definition of Laplace transform and doing all sorts of integration by parts or whatever, we can just apply this rule if we already know the Laplace transform of little f. So for instance, I have just a few examples here with some basic functions. So suppose little f was some exponential function e to the at, where a is some number, a is some constant. So hopefully you recall this, right, that the Laplace transform of little f here, the Laplace transform of e to the at, which is going to be my capital F of s, was 1 over s minus a. Or you could also think of this as s minus a to the negative first power. Well, then I could apply this rule with different powers of t, right? Then applying this rule, the Laplace transform of, say, t to the first times f of t times e to the at would just be negative 1 to the first power, so negative 1, times the first derivative of f of s with respect to s. Well, there's f of s. The first derivative would be the following, right? So I have negative 1, and then this first derivative of f of s would be, negative 1 times s minus a to the negative second. So we'd get, positive 1 over the quantity s minus a squared. And there would be there's the Laplace transform of t times e to the at. And I could keep going with this, the Laplace transform of this function, say t squared times e to the at. Again, according to the rule, the value of n is 2 here. This would be negative 1 squared, right, negative 1 to the nth, times the second derivative of f of s with respect to s. Well, negative 1 squared is just positive 1, so what I end up with here is just the second derivative of f of s. Well, we know the first derivative here, right? That's the first derivative that I just double underlined. So the second derivative would be positive 2 times s minus a to the negative third, right? Or 2 over the quantity s minus a cubed. And there's the Laplace transform of t squared times e to the at for any value of a. Great. And again, you could keep going with this. Make it do t cubed would be just times e to the at would be negative negative 1 times the third derivative of f of s, and so on. All right, so let's go with another example. So here again, I'm just going to keep the rule up here for you. Now suppose little f of t was the sine of kt, where k is some constant, sine of 2t, sine of 3t, etc. Now again, hopefully you recall that the Laplace transform of my little f of t here, the sine of kt, that's going to be my capital F of s, right? This capital F of s here. Remember, for sine of kt, the Laplace transform was k divided by s squared plus k squared, right? Or if you'd like to make the derivatives maybe a little easier, k times the quantity s squared plus k squared to the negative first power. Same thing. So then, following the rule, right, we could multiply the sine of kt by some whole number power of t and pretty easily figure out the Laplace transform, right? The Laplace transform then of t to the first times the sine of kt would be negative 1 to the first, or just negative 1, times the first derivative of f of s with respect to s. So this would be negative 1, and then this first derivative again would be negative k times s squared plus k squared to the negative second, and then using the chain rule, right, so with respect to s here, times the derivative of s squared plus k squared, that would just be 2s, right? Remember, k is going to be a constant here. So if I wanted to rewrite this, this would be positive k times 2s. So this would be 2sk in the numerator divided by s squared, the quantity s squared plus k squared squared in the denominator. All right, and so on, right? I'm not going to do too many of these. I just want to introduce it to you, and then we'll get to more examples. So if I had t squared times the sine of kt, it would just be the second derivative, negative 1 to the second, which is positive 1, times the second derivative of f of s with respect to s. So I would basically just take this. Now, if I was doing the second derivative, I'd have to use the product rule, or if I was looking at this, I'd have to use the quotient rule, right? Because the numerator and denominator both have function expressions that depend on s. All right, and then in a similar fashion, suppose my little f of t, right, this little f of t here, suppose it was the cosine of kt, where again k is a constant. One more time, I'm hoping you recall that the Laplace transform of the cosine of kt is the following. Let me just write it out here. This will be my capital F of s. And remember, this was s divided by, and then s squared plus k squared. Or you could write it as s times, the quantity s squared plus k squared to the negative first. Now, I'm just going to leave it like this and use the quotient rule when I do the derivative. So then applying the rule, I know the rule is kind of off screen now, but you've seen it a couple times now. The Laplace transform of, t to the first times the cosine of kt would be -1 to the first times the derivative of, f of s, the Laplace transform of the cosine of kt with respect to s. So this is -1 times, and then here I'm going to do the quotient rule. So we have, denominator times the derivative of the numerator with respect to s would just be 1 minus the numerator times the derivative of the denominator with respect to s would just be 2s, and all this divided by the denominator squared. Right. And then doing a little simplifying here, this is s squared plus k squared minus 2s squared. Well, that's s squared, minus 2. That'd be this up top, right? This numerator would just be k squared minus s squared then, right? But then it's being multiplied by -1 here, so I end up with s squared minus k squared in the numerator divided by the quantity s squared plus k squared squared in the denominator, and there's the Laplace transform of t times cosine of kt. All right, and then for the, if I had t squared, it'd be -1 squared times the second derivative of this f of s with respect to s. So I would basically take this here, this k minus s squared over s plus k squared, take the derivative of that again. All right, so a little more involved, a lot more s terms involved with the cosines. All right. Okay, so after those, let's get into some actual specific examples now. All right, so my first example is kind of like what I had here in this exponential function section. And for the rest of the examples in the video, I'm asked to evaluate the given Laplace transform. So you see I have t, right, some power of t, whole number power of t, times, and then, an exponential. Now this exponential, that's going to be the little f of t here from the rule. Right? So little f of t is e to the -10t. And off to the side here, the Laplace transform of, e to the -10t on its own, right, that's going to be the capital F of s, would be just 1 over s minus -10, right? Just replacing a with -10 from earlier. So that's 1 over s plus 10, or to make the derivatives easier, right, s plus 10 to the -1st. And then according to our rule, the Laplace transform of, t to the first, right, t to the first, n is 1, times this e to the -10t would be -1 to the first times the first derivative of f of s, which I found over here, with respect to s. So this is -1, and then this first derivative of f of s with respect to s would be -1 times s plus 10 to the -2. So I end up with +1 over the quantity s plus 10 squared. And there you have it. That is the Laplace transform of t times e to the -10t. Wonderful. Right. And again, it's a lot quicker to use, if you had this rule down, if you know what this rule is, it's a lot quicker. I mean, you could also do it using the definition of Laplace transform, right? Evaluating that improper integral from 0 to infinity, but this is obviously much faster. All right, another one here. Again, same instruction, right? Evaluate the given Laplace transform. So here I have, another power of t, right? T to the nth, t to the third, so n is 3. And then the little f of t is just e to the t, right? The little f of t. All right, so off to the side, the Laplace transform of just e to the t, that's going to be the capital F of s, and that is just 1 over s minus 1. Or, to make derivatives easier, s minus 1 to the negative first power. And then applying the rule for our derivatives, transforms involving derivatives here, this will be equal to the negative 1 to the third power, right, which is going to just be negative 1, times the third derivative of f of s with respect to s. Okay. So let's do let's go over here off to the side. Let's do the first derivative, f prime of s, would be negative 1 times s minus 1 to the negative second. The second derivative with respect to s, f double prime here, would be positive 2 times s minus 1 to the negative third. And then the third derivative, which is what's being asked for here, is going to be negative 6 times s minus 1 to the negative fourth. And putting this stuff all together, we'd have negative 1 times negative 6, that's positive 6, times s minus 1 to the negative fourth, so that's divided by the quantity s minus 1 to the fourth. And there you have it. All right. Hopefully simple enough. Okay, next example. Same instructions. So again, I have a power of t to the first multiplied by the cosine of 2t. So just as before, this cosine of 2t is the little f of t, and then off to the side, let's do the Laplace transform. Right? The Laplace transform of little f, right? This cosine of 2t is just, remember this is s divided by s squared plus 2 squared. The value of k from earlier is 2. So it's s divided by s squared plus 4. And this is the capital F of s. And since I have t to the first power in here, my resulting Laplace transform is going to be, negative 1 to the first multiplied by the first derivative of f, capital F, with respect to s. Let me just find that over here. I'll call it f prime. So again, I'll leave it this way. Do the quotient rule. We have denominator times the derivative of the numerator with respect to s would just be 1 minus, and then the numerator times the derivative of the denominator with respect to s. And this is from earlier. Remember, this is going to end up being k squared minus s squared, or 4 minus s squared. And then divided by the denominator squared, s squared plus 4 squared. So we end up with 4 minus s squared in the numerator, divided by s squared plus 4, that quantity squared in the denominator. But then again, this first derivative is getting multiplied by negative 1. So that'll make the numerator s squared minus 4 divided by, and then the quantity s squared plus 4 squared. And there's your Laplace transform of t times the cosine of 2t. Alright, and I've got one final example where I'm going to be assuming here also, now that, again, you've done previous videos on the some special translation theorems for Laplace transforms. So I'm going to be assuming in this last example that you recall what the first translation theorem was, translation about the s-axis, because that's going to come into play in this final example. Alright, so again, I have just t to the first power. So the rest of it, right, e to the 2t times the sine of 6t, that's going to be my little f. And then off to the side, Laplace transform of e to the 2t times the sine of 6t. I'm going to get using the first translation theorem. Now maybe this will help ring a bell on what the first translation theorem says. Remember, the first translation theorem had to do with Laplace transforms of functions being multiplied by exponentials. Right, e to the at. If you recall, the Laplace transform of just the sine of 6t, that would be 6 over s squared plus 36. And then for this 6 sine of 6t times e to the 2t, I just replace s with s minus 2. Right, just do the function of s, but with s minus 2 as the input instead. So this is going to be 6 over, and then instead of s squared plus 36, s plus 2, s minus 2 squared plus 36. Alright, and I guess if you want to multiply this out, you can. So this would be 6 divided by, and then you have s squared minus 4s, and then plus 40. Okay, and this is the capital F of s that comes up in the rule for this derivatives of transforms. Alright, so now that we use that first translation theorem, right, yeah, I should probably write that so you can go look it up. Alright, so this is applying the first translation theorem. I got that result. Alright, and then applying this rule for derivatives of transforms here, the Laplace transform of t to the first times this would again just be negative 1 to the first times the first derivative of, capital F of s, where this is capital F of s. Now, just as with previous examples, because there's a constant in the numerator, I'm going to write this way. This is going to be 6 times the quantity s squared minus 4s plus 40 to the negative 1. So now when I do the first derivative, right, capital F prime here, it's just negative 6 times s squared minus 4s plus 40 to the negative second, but then also times 2s minus 4. Right, the derivative of the s squared minus 4s plus 40. And you could factor a 2 out of this factor also. Putting it with this would make that negative 12, and don't forget this is being multiplied by negative 1, so it ends up being positive 12 times s minus 2. Right, that s minus 2 came from factoring a 2 out of this, 2s minus 4. Pull a 2 out, you make that negative 12, and then you have s minus 2 left, and then multiplying by the negative 1 gives you positive 12. That's all in the numerator, and then I have in the denominator s squared minus 4s plus 40 squared. Right? Or if you'd like, you could rewrite this as s minus 2 squared plus 36. That's the same thing, right? So there we go. There's the Laplace transform of t times e to the 2t times the sine of 6t. Which again, you could do this the long way. You could always use the definition of Laplace transform to try to find this, and you could probably manage. But you'll notice that when you do that, though, it'll involve integration by parts several times over. It would take quite a while for most people to find the Laplace transform using the definition. This is obviously much quicker when we know certain rules, the first translation theorem and this derivatives of transforms rule or theorem. Okay, and that's all I've got for you. Hopefully the rule made some sense and my use of the rule was clear. And I'm hoping that watching me go through these several examples helps you out when you're working on problems like this on your own. And thank you very much for watching.